To help us develop an even deeper understanding of what's going on here, we're going to go ahead and make one further assumption. We're going to go ahead and assume that the two electromagnetic waves are identical. In other words, they have the same intensity, which also means that they have to have the same magnitude of the electric field. In that case, what we end up getting is that the irradiance is this right here, or if we recognize that C epsilon naught times E naught squared is simply the irradiance of each of the beams by themselves, this is what we end up with for our total radiance. So just a few things to notice and take a look at with this. These are the sorts of questions that you really want to ask yourself when looking at an equation. Try to understand what exactly is going on. And so the first thing we're going to want to do is ask when and what is the maximum value of I? What's the maximum irradiance that we can possibly get? When does this occur? And what exactly is going on under this circumstance? The other thing that we'll be interested in is the minimum value. What's the minimum value that I can have? Where does this occur, and what exactly is going on? So whenever you come across equations, you really want to ask yourself this. Try to look at the limiting cases. What are the maximum? What are the minimum? What's happening? When does this occur? Just get in the habit of asking these equations. And so let's go ahead and answer those equations. So looking at my equation for the irradiance, well, the maximum is going to occur whenever cosine delta is at a maximum, which is when it has a value of 1. And in that instance, we have an irradiance of 4 times the irradiance of each of the electromagnetic waves by themselves. So where does this occur? Well, cosine of delta is 1 whenever delta is some integer number of 2 pi. Another way of looking at this is that when the path length difference is some integer number of wavelengths, then we will get a maximum irradiance. In other words, when that path length difference is some integer times lambda. And so this is essentially constructive interference. And at this point, the two waves line up, and the peaks line up with the peaks, the valleys line up with the valleys. And so if we're looking at the wave fronts of the individual waves, we can see that those wave fronts are essentially overlapping with one another. And so I'm just drawing in the wave fronts at the peaks, and so they perfectly overlap. Now, one question you might want to ask yourself at this point is, well, if energy is really conserved, how in the world can the irradiance be 4 times the irradiance? We only have 2 beams here. How are we getting 4 times the brightness that we would under normal circumstances? All right, so for the minimum, then, that's going to occur when the cosine of delta is -1. And under that case, we get an irradiance of 0. In other words, there's no brightness. Just see a dark spot. Nothing is going on there. So this occurs when delta, that phase difference, is some half integer number of 2 pi. Or another way of looking at that is that the path length difference is a half integer number of wavelengths. The two waves have traveled a difference in paths that corresponds to half of a wavelength. And so this is essentially destructive interference. And so the two waves are canceling each other out. And if we look at the wave fronts, we can see that the wave fronts for this guy are exactly half a wavelength out of phase with the wave fronts from the other wave. And so these wave fronts are essentially shifted relative to one another by lambda over 2. So another question to ask yourself is, if energy really is conserved, how is it that we have absolutely no brightness here, right? Where did that energy go? It has to be conserved, so where is it?